Dear students, in the first lecture of organometallic chemistry, we have discussed what is meant by organometallic compounds. Now, today we are going to discuss the classification of organometallic compounds. With the help of various waves, there is classification of organometallic compounds. So let us explain in details. Today, continue the classification of organometallic compound. So this is based on nature of metal carbon bond which is present in organometallic compound. So ionic organometallic compounds we are going to discuss. We know that ionic bond means the bond between cation and anion, that is the electrostatic force of attraction between positively charged ion and negatively charged ion. So these compounds contains highly electropositive metals such as alkali metals, alkaline earth metals, lanthanides and actinides having electronegativity equal to or less than 1, and hence they are ionic in nature. Carbon atom is negatively charged and metal atom is positively charged in these compounds, and hence there is electrostatic force of attraction between this metal ion and carbon atom, and in this way ionic bond is present in this compound. Therefore they are called as ionic organometallic compound. These are the examples: methyl potassium. See, potassium is positively charged and in methyl there is a negative charge, and hence there is electrostatic force of attraction between carbon and potassium. This is another example: sodium cyclopentadienyl. So on this cyclopentadienyl there is negative charge and on sodium there is positive charge, and hence there is a formation of the bond, ionic bond between sodium and cyclopentadienyl, that is carbon. What are the properties of these compounds? So see, first these are colorless compounds, or ionic organometallic compounds are colorless. Next property, these are highly reactive with air, water and protic reagents. Okay, so show high reaction with these air, water and protic reagents. Next one, there is reaction with water. That means they are hydrolyzed by water, and at that time there is formation of hydroxide and hydrocarbon. Example, see this potassium methyl. Here this potassium methyl is hydrolyzed by water and there is formation of hydrocarbon, that means methane, and potassium hydroxide is the byproduct. Second example, this is dimethyl zinc. So this organometallic compound reacts with water. There is formation of again methane, hydrocarbon and zinc hydroxide. These ionic organometallic compounds are non-volatile solids. Next property, they are insoluble in hydrocarbon solvents. These are prepared in ethereal solvents such as diethyl ether and THF. THF means tetrahydrofuran. Next one, this is about stability. The stability of ionic organometallic compound increases with increase in stability of the carbanion. So carbanion of sodium cyclopentadienide, that is C5H5 minus ion, is stabilized by resonance, and hence the stability of this compound is increases, and in this way it is shown how this carbanion ion is stabilized with the help of resonance. Then see second type of organometallic compound, which is called as sigma bonded covalent organometallic compounds. In these compounds, the name indicates that in between carbon and metal, now there is formation of covalent bond. We know that how covalent bond is formed. There is sharing of electrons between carbon and metal. Okay, so covalent bond is present in this organometallic compound. Therefore, it is called as covalent or sigma bonded organometallic compound. So see this, in these compounds, the carbon atom of organic group is attached to metal by a normal covalent sigma bond. It is two center, two electron. Two center, one is metal atom and another is carbon. And there is presence of two electrons between these two. Generally, p block elements having electronegativity greater than 1 but less than 2.5 forms this type of organometallic compounds. 2.5 is the electronegativity of carbon, and metal have electronegativity less than carbon but greater than 1. Okay, they form such type of compounds. These are the examples from this category. So trimethyl boron, this is the dimetallic structure of trimethyl aluminum, then tetramethyl silicon, tetramethyl lead. Remember, some D block elements also form such type of compound, that is sigma bonded covalent organometallic compounds. These are the examples. This is hexamethyl tungsten. This is manganese compound. This is tantalum compound. This is pentamethyl tantalum. All these are examples from this category. How this covalent bond? Before discussing the next point, remember well, carbon atom is present in organic ligand. In the formation of covalent bond with metal, what happens? Carbon undergoes sp3 hybridization. We know that the electronic configuration of carbon is 2s2, 2p2. The 2s electron is promoted to 2p orbital. So 2s orbital contains 1 electron and 2p orbital now contains 3 unpaired electrons. So totally there are 4 singly electrons are present in 1s and 3p orbitals, which combines and carbon atom undergoes sp3 hybridization. This is very important. So remember well, carbon undergoes sp3 hybridization. Each sp3 hybrid orbital contains 1 electron. Later on, this sp3 hybrid orbital of carbon overlap with metal's singly occupied hybrid orbital, and there is formation of the covalent bond, sigma bond between metal and carbon. So see this, the singly occupied hybrid orbital of carbon atom of organic group overlap with singly occupied hybrid orbital of metal atom, and there is formation of 2 center 2 electron bond. Now, the shape of this organometallic compound depends on type of hybridization. Here, first one, if metal undergoes sp hybridization, then organometallic compound is linear. This is the example. Beryllium undergoes sp hybridization and it overlaps with sp3 hybrid orbital of carbon, and there is formation of bond between beryllium and carbon. So the shape of that organometallic compound is linear. When hybridization is sp2, the structure, the shape of organometallic compound is triangular planar. Here, this is the example, trimethyl boron. Boron undergoes sp2 hybridization. Then this sp2 hybrid orbital of boron overlaps with carbon's sp3 hybrid orbital. There is formation of sigma bond, and the shape of organometallic compound is triangular planar. Next one, if a metal undergoes sp3 hybridization and it overlap with that sp3 hybrid orbital of metal, here there is example silicon. Okay, silicon undergoes sp3 hybridization. This sp3 hybrid orbital of silicon overlap with sp3 hybrid orbital of carbon, and there is formation of bond between silicon and carbon. In this way, here the shape of organometallic compound is tetrahedral. Let us see. Let us discuss in detail how the bonds are formed between carbon and metal. This is the first example, dimethyl beryllium. We know that atomic number of beryllium is 4. Electronic configuration is 1s2, 2s2. So in ground state, electronic configuration 2s contains 2 electron, 2p contains no electron. In excited state, this 2s electron is promoted into 2p orbital. So now 1 electron is present in 2s and 1 electron is present in 2p orbital. These two orbitals combine together, that means there is hybridization sp in this way. This sp orbital of beryllium overlap with sp3 hybrid orbital of carbon, and there is formation of sigma bond between beryllium and carbon. Similarly, other sp hybrid orbital of beryllium overlaps with sp3 hybrid orbital of carbon, and hence there is formation of sigma bond between beryllium and carbon. And this is the shape of this dimethyl beryllium, which is linear. The bond angle between beryllium and this methyl group is 180 degree. So it indicates that the shape is linear. Next compound, trimethyl boron. Here the atomic number of boron is 5. Electronic configuration is 1s2, 2s2, 2p1. So in ground state, 2s contains 2 electron, 2p contains 1 electron. In excited state, 2s electron is promoted into 2p orbital. Now there are 3 unpaired electron. In 2s contains 1 electron, 2p contains 2 electron. These 3 orbitals combined together undergoes sp2 hybridization. This sp2 hybrid orbitals contains 1 electron, 1 unpaired electron. So sp2 hybrid orbital of boron overlap with sp3 hybrid orbital of carbon, and there is formation of sigma bond between boron and methyl group. This is first bond. Then see this second bond, again sp2 hybrid orbital of boron overlap with sp3 hybrid orbital of carbon, and there is formation of second sigma bond. In this way, this is third bond. From boron, sp2 hybrid orbital overlap with sp3 orbital of carbon, there is formation of sigma bond. In this way, 3 bonds are formed between boron and carbon, boron and carbon of methyl group, and hence this trimethyl boron has triangular planar shape. Okay, so when there is sp2 hybridization, the shape of organometallic compound is triangular planar. Here the bond angle is 120 degree. Then see next compound. This is tetramethyl silicon. The electronic configuration of silicon is 3s2, 3p2. In ground state, 3s contains 2 electron, 3p contains 2 unpaired electron. In excited state, this 3s electron is promoted into 3p orbital. Now there are 4 unpaired electron, 1 in 3s and 3 are present in p orbital. These 4 orbitals combine together and shows sp3 hybridization. So sp3 hybrid orbital of silicon overlap with sp3 hybrid orbital of carbon from methyl group. First sigma bond is formed. This is the formation of second bond. sp3 hybrid orbital of silicon overlap with sp3 hybrid orbital of carbon, there is formation of second sigma bond. This is the third bond. sp3 hybrid orbital of silicon overlap with sp3 hybrid orbital of carbon, there is formation of third sigma bond. And see the last bond again. So sp3 hybrid orbital of silicon as well as carbon overlaps with each other, there is formation of fourth sigma bond, and hence this is the structure of this tetramethyl silicon, which is tetrahedral, and at the corners of tetrahedron 4 methyl groups are situated, and at the center of tetrahedron there is silicon. Okay, so when there is sp3 hybridization, at that time the shape of organometallic compound is tetrahedral. Now see the percentage of ionic character in metal carbon bond, it is increases with decrease in electronegativity of metal atom present in organometallic compound. See with this table, first bond between silicon and carbon, electronegativity of silicon is 1.8, and at that time percentage of ionic character is 12. Now when we move from silicon to aluminum, what happened? In this bond the electronegativity of aluminum is decreases 1.5, and hence ionic character between bond is increases, it is now 22. Again the electronegativity of magnesium, it is decreases to 1.5. Okay, in this bond magnesium carbon, it is decreases to 1.2, and hence ionic character is increases to 35. Similarly in this bond sodium carbon, the electronegativity decreases to 1 unit and the ionic character is very high, that is 47. So percentage of ionic character in metal carbon bond increases with decrease in electronegativity of metal atom. Now see third type of bond in organometallic compound, pi bonded covalent organic metallic compounds. So here what happened, pi bond is present between carbon atom and metal atom. So organic groups like ethylene, acetylene, cyclopentadienyl, benzene have pi molecular orbitals. These pi molecular orbitals interact with atomic orbitals of transition metal atom, and there is formation of pi bond. So these compounds or these molecular orbitals are called as pi bonded covalent organometallic compounds. So pi bond is present. Example, ferrocene. In ferrocene, iron is the metal atom. It reacted with the pentadienyl, cyclopentadienyl. How the bond is formed? See, atomic orbitals of iron interact with pi molecular orbitals of cyclopentadienyl, and there is formation of molecular orbitals of the molecule. In this way, ferrocene compound is formed, and ferrocene is called as pi bonded covalent organometallic compound. Then see electron deficient organometallic compounds with bridged multi-center bonds. Multi-center, that means more than 2 centers are present in this compound, as well as there is a bridge is present in this compound. So in some organometallic compounds, alkyl or aryl groups acts as bridging ligand. Example, polymeric dimethyl beryllium. Okay. Second example, a dimeric trimethyl aluminum. This is the dimeric structure. See the structure of polymeric dimethyl beryllium. Here see there is a bridge between these two beryllium atoms with the help of methyl group. So methyl group acts as bridging atom between two beryllium atoms. The bond length is 1.93 angstrom unit between methyl and beryllium. Also here the bond length is the same, 1.93 angstrom unit. This bond angle is 66 degree while this is 114 degree. Here it is 2.09 angstrom unit while this is 3.15 angstrom unit. So these units are joined together, combined together, there is formation of polymer, therefore it is called as polymeric dimethyl beryllium. Carbon atom of bridging alkyl or aryl group present at equal distances of metal atoms. That means this distance is equal throughout the chain. Then see second example. So Al2CH36, central atom is aluminium, electronic configuration is 3s2 3p1. In ground state, the configuration of aluminium is 3s contains 2 electron, 3p contains 1 electron. So aluminium in ground state contains 2 electron in 3s orbital and 1 electron in 3p orbital. In excited state, 3s electron is promoted into 3p orbital, and now there are 3 electrons unpaired present in orbitals. So these 4 hybrid orbitals, combined together, 1 3s and 3p orbitals combined together undergo sp3 hybridization, okay, and there is formation of 4 hybrid orbitals. Out of these, 3 are half-filled and 4th is vacant. There are 2 aluminium atoms, and these 2 aluminium atoms form 4 hybrid orbitals. 3 are half-filled, so this is first, second, third. 3 sp3 hybrid orbitals are half-filled and 4th one is vacant. Similarly, this aluminium, this forms 1, 2 and 3 half-filled sp3 orbitals and 4th one is vacant. There are 4 methyl groups, 1, 2. This one is third, this one is fourth. These 4 methyl groups are called as terminal methyl groups, and these 2 methyl groups, they are acts as bridged methyl group. How the bond is formed? First, let us discuss about terminal methyl group. So from this methyl group, carbon is sp3 hybridized, okay, is undergoes sp3 hybridization. So one sp3 hybrid orbital overlaps with sp3 hybrid orbital of aluminium, and there is formation of sigma bond. Similarly, this one, aluminium's sp3 hybrid orbital overlaps with sp3 hybrid orbital of carbon, there is formation of sigma bond. Similarly, for this second aluminium atom, this sp3 hybrid orbital overlaps with hybrid orbital of carbon, and there is formation of third sigma bond. Similarly here, sp3 hybrid orbital of aluminium overlap with sp3 hybrid orbital of carbon, and there is formation of sigma bond. Now see here, from this aluminium, this is vacant hybrid orbital. It overlaps with half-filled sp3 hybrid orbital of carbon as well as half-filled sp3 hybrid orbital of aluminium. Hence, there is formation of 3 center 2 electron bond. So 2 center means 2 aluminum atom, and third one is methyl, that is carbon from methyl. So in this way, aluminium, methyl and aluminium, this electron deficient bond is formed. This is 3 center 2 electron bond. Similar in case of this, from this aluminium, this is half-filled. From this aluminium, this is vacant orbital, and these 2 orbital overlaps with sp3 hybrid orbital of carbon, and there is formation of 3 center 2 electron deficient bond. Agreed? And this is the structure of this dimeric structure. Two aluminum atoms are present, and in between these two aluminum, this methyl as well as this methyl forms a bridge between these two aluminum atoms. These are called as bridged atom. These 4, 1, 2, 3 and 4, these 4 methyl groups acts as terminal methyl group. So this is about the structure of Al2CH3 dimeric structure. In next lecture, we are going to discuss about 18 electron rule. So we conclude here this lecture. Thank you.